Hi everyone, this is a video on the Bonferroin method for multiple hypothesis testing. I'm going to go over just the general reason of why we should care about this, the theoretical motivation behind the adjustment, and how to do the adjustment in practice. So in practice, what happens is when we test a lot of individual hypotheses for, so let's say each hypothesis is denoted H naught I, H naught superscript I, that's one of our hypotheses, and we have I equals 1 all the way to M total hypotheses, and there is a corresponding PI, which is the p-value. And let's say Ri is probability of, let's just say Ri is the event H naught I gets rejected. So in practice, if we take a lot of individual hypothesis tests, let's say 1,000 tests, and 75 tests are significant, and let's say alpha was equal to 0.05, then in an individual testing situation, we would expect that 5% of 1,000 will be false discoveries or will be type 1 errors. What does this mean? That 50 of the tests, which is 5% of 1,000, are going to be junk. They're going to register as significant when they're not actually significant. And that's because when we set our alpha level, we have this probability that we reject the test Ri, given that H naught I is true, is equal to alpha. So see, we have a normal standard deviation. There's going to be areas where we will have data that actually falls into those areas. These areas are the Ri areas. But that data was true and it was correct, and the null hypothesis is still correct. So when we do individual testing, we could get into this situation where most of our significant differences actually aren't significant. And this happens a lot in biology. And so that could be a really big problem for results. Versus in multiple hypothesis testing, instead, our goal is to control the rate of false discoveries. So again, assuming that we have 1,000 tests, 75% are significant, and we set alpha equal to 0.05. Instead, what we are trying to control is the family-wise error rate, or the error rate overall. So instead, we expect 5% of 75 will be type 1 errors, or roughly 3.75. So of those 75 results that we would get with multiple hypothesis testing, we'd expect only 4 of them to be garbage or not actual true significant differences. So how do we do that? How did I get these numbers, and what's the motivation? So theoretically, this all comes from the Bonferroin distribution, or the Bonferroin inequality. Now, if we're looking just at the individual situation, so this guy right here, yes, that individual test has this rate. But instead, if we considered a group situation, So the probability of R1 or R2 or R3, R3, dot, 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 all the way to Rm, given all H0 are true, by the Bonferroin inequality, which is how I get this. This is actually just the sum. It is the upper bound of this probability is the sum of all of these probabilities individually. And the sum of these all individually, I equals 1, is the sum of all these alphas, which is alpha times m. That's the group type 1 error rate if we do no adjustments. So instead, consider looking at the individual testing rates, not using this criteria, but still set an alpha value, but instead do individual tests at alpha divided by m. When we use this, then the probability, I'm just going to copy this right here. Ends up being the sum I equals 1 to m, alpha divided by m, which becomes alpha. And then our group error rate, type 1 error rate, type 1, is then alpha. So in practice, this is exactly what you're going to do. You'll have your individual hypothesis testing. You'll calculate that individual p-value for each hypothesis, and instead of for checking alpha, you're just going to check alpha over m. It's really just that simple. And if this happens, then you will reject H0 superscript I. This is just adjusting the significance level. What I see more often than not is people actually just adjusting the p-value. So they have some marking to make it adjusted, which is just the p-value times n, and they check that it's less than alpha, and if so, they reject H0. So you still look at these tests individually, you just do this adjustment so that way you're controlling the overall type 1 error rate instead of the individual type 1 error rate. And it gives you a much stronger interpretation and stronger results. It's not impossible to, have wonderful results and that all of your significant differences stay the same. But oftentimes, once you use the correction, you won't have 75 significant individually and 75 significant multiple testing. You would see a drop pretty often. But anyways, that's the end of the video. Please let me know questions, comments, or concerns.